Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Srikant will be speaking here. I've had the pleasure of watching the progress of this work over the years, both here and visiting in India, and with his student, Archana Ravindar, who could not be here today. By way of introduction, Srikant is currently the chairman of computer science and automation at the Indian Institute of Science in Bangalore, received BE in electronics from Bangalore University, and Masters of Engineering and PhDs in computer science from the IISc. He's a recipient of Young Scientist Medal of the Indian National Science Academy, and his areas of interest are compiler design and software components, and obviously the material here at hand in regarding memory management and garbage collection. It's a pleasure to have you here. Thanks.
Thank you, Mark, for the nice introduction, and good morning to all of you. So this is the thesis work of my student Archana, who couldn't be here because she has finished her degree and left the institute. So unfortunately, she was not able to make it. So as one of our friends here from Karlsruhe, Professor Padberg, put it, the hard work was done by Archana, and I'm doing the marketing. So the project is about garbage collection. We started off looking at the rotor garbage collector, which is a stop-the-world garbage collector. And then, the first obvious way of improving garbage collection, which is stop-the-world variety, is to make it concurrent, of course. But then, that's definitely not sufficient. So we need other methods, other techniques in order to make the garbage collector more efficient. So to begin with, the cluster allocation, basically, in other words, if you have a collection of objects in the program which is created due to data structures which are formed and so on and so forth, it's always possible to find out by compiler analysis, which is of course conservative, that these are actually clusters of data which are born in some way together and then die together. Once we do that, allocation of space for these clusters could be done separately, and the garbage collection cost will automatically come down. That's the theme of the project. So let's see how it goes further. To emphasize why all this is required, let's look at a graph which shows the impact of long-living objects on garbage collection. Well, it's fairly easy to find out that the scavenging of long-life objects, really impacts for a significant amount of the garbage collection time. So this graph, you can easily see it's somewhere around 40 to 50% of the average. This time in garbage collection is spent on just the scavenging part. And then how do we reduce the garbage collection time? That's by trying to reduce the scavenge time in garbage collection. So if you look at it, we can compute the lifetime of objects and then bind them to the activation record of a method that uses them last. So once we do that, we are able to say, look, the method will terminate, and therefore the space actually which is occupied by that object will be released as soon as the method terminates. So this can handle volatile objects very well, but it cannot handle long-living objects which are referred to by several methods. The stack allocation scheme is used for such objects because they are born and die within that particular method, and we don't really use heap allocation. If you use heap allocation, then the garbage collector has to look at those objects. That's the problem. And then it cannot handle related objects. This I just mentioned just now. Related objects that refer to each other from different methods, but they die together, similar to the dynamic data structures. So what do? We detect long-living clusters and allocate them separately. So what are the highlights of a cluster allocation scheme? Well, first of all, as I already mentioned, we identify long-living clusters of objects and allocate them in what is known as a mature object space. It's not the normal heap. And we don't do any garbage collection on the mature object space. So, and we recover the whole mature object space at once at method termination time. This actually avoids tracing and copying of long living objects. So thereby it reduces the total garbage collection time. And of course, it reduces heap size. So we will see the amount of reduction that's possible in a short while. The heap will now contain just objects with shorter lifetimes. So obviously the GC time comes down. And compiler analysis to identify clusters is possible, but obviously these are conservative. There will be the conservative estimates are reasonably okay, but definitely possible to improve it in the future. So there will be no overheads at runtime. Yes, please.
When the program terminates, or
the method terminates.
Or when a method terminates. Yeah.
So what is the approach? The approach is to use information about lifetimes of objects, and we construct what is known as a points to escape graph. And this is based on the compositional pointer analysis and escape analysis framework of Valley and Reiner, which is fairly well known. The longest living methods that contribute to long living clusters are identified using a profiling scheme. So now put the two together. You detect clusters and you detect long living methods, and you say, okay, here is a group of methods which actually make dynamic data structures, and they are very long living. So let's allocate the space for these structures in a different place. So objects that do not escape the longest living methods are the roots of clusters. That's the basic idea. So all objects which are reachable from the roots of clusters belong to the clusters. And this idea was actually proposed by Hayes, and he called it key objects. But in the paper, they did not propose a way to detect key objects automatically. It was actually identified by the programmer. Or some other papers later actually identified them during runtime. So all the cluster objects are statically allocated in a separate mature object space, and when the method which actually binds the lifetime of root objects returns, the entire cluster is garbage, and therefore it is reclaimed in its entirety. The evaluation of is done actually using a baseline GC that runs in stop the world and concurrent modes. And of course, even the baseline GC was compared to the stop the world scheme of rotor. The whole thing was implemented in rotor, and both cluster and stack allocation. You see, these are two slightly different things. As I mentioned, we can, for each object which is within the method, you could use stack allocation, and which are objects for which they are actually accessed across methods, we could use a cluster allocation scheme. Both have been implemented and tried out. So very briefly, let's look at the compositional pointer and escape analysis. It's a fairly straightforward method to understand, but not so easy to implement. Determines for every allocation site the method M whose stack frame will outlive the object created at the site A. So that's the basic idea. So to do this, we construct the PTE graph. And how do we do that? The object P escapes a method if it is a formal parameter, obviously, because it's given to you by somebody, the formal parameter. A reference to P is written into a static variable, so we don't know how the static variable will be used by others. A reference to P is passed to one of the callees of M, say N, and we don't know what N did to P. In other words, I give you the object, and I don't know what you do with it. And of course, M returns P. I just give it to somebody else, and then I don't know what happens. So if none of the above, then actually M captures P. So P actually does not go outside M at all. The method M can actually allocate the space for P on the stack, and if they are cross clusters and so on and so forth, then we can allocate it on the mature object space and so on and so forth. Now, there are two analyses which are required. One is the intra-procedural analysis, and the other is the inter-procedural analysis. So to create the PTE graph, the PTE graph itself is straightforward to explain. the objects are nodes, and references between objects are all the edges. So there are two types of nodes and two types of edges: inside nodes, inside edges and outside edges. Inside nodes are created within the currently analyzed region, whereas outside nodes are outside the currently analyzed region. Similarly, the inside edges and outside edges can also be classified. So we create the graph. The intra-procedural method algorithm incrementally computes the PTE graph statement by statement. And obviously, for some procedures whose graphs haven't been created, there would be holes. So these holes are actually filled by the intra-procedural algorithm, which puts these graphs together one by one. Let's look at a simple example. There is no need to remember the entire program segment. Just notice that there are a couple of objects, dict, TSB, then SB, M, ISTR, AGM, and so on and so forth. And in the picture, this is something, for example, here is one method, run, the other method, read file. And these are the outside edges, these two, and these are all the inside edges. These yellow nodes are all inside nodes, and the black ones are all outside nodes. So to begin with, in this read file procedure, only this part of the graph gets created, and then during the intra-procedural analysis, these edges are actually added. So that's how it is. Now, the SIF node, which is here, is captured within the procedure, the method, because there is nothing pointing to that particular thing. And then all others really escape the read file method. This is only a part of the picture. That's it. That's why it's not very clear how they escape. But you can take it that these actually, because they are accessed from here as well, all of them actually escape the method. This node AGM, which is here, actually links to this node during the interprocedural analysis, and AGM is also the root of a cluster. There are no pointers pointing to edges pointing to AGM itself, and that would be the root of a cluster which resides inside the run method. Okay. So how do we identify clusters? So first of all, you apply profiling and get a list of methods that have a long life. Long life is obviously qualitative, so you could actually see what you mean by long life, experiment with the life of how much should the length be, and so on and so forth. And we choose methods which are close to main. And then the emphasis is on those methods which live long and the objects that are potential roots of clusters. So that's what I said, long-living methods and those who actually make clusters. These are the two important things. And nodes with no incoming edges are the roots of clusters, and depth first search on the PTE graphs is adequate to identify these clusters. So we just identify what hangs from each of these roots. Once we do that, only edges corresponding to new statements need to be looked at, and all objects created by such statements are allocated using a different allocator, new1 instead of new. So new1 allocates the objects in a mature object space. It doesn't allocate them on the regular heap. So now our experimental setup. To begin with, we built a concurrent garbage collector, and the existing one is this top-the-world scheme. Ours is a generational, nothing very special. It's not that there is something terribly new about this garbage collector. It's actually the Nettles and O'Toole scheme, which came out quite some time ago. It actually is a generational garbage collector, and it has two generations, young and old. And of course, most important is it has exactly the same GC interface as the rotor GC. Otherwise, it's not easy to plug it in. So this is the block diagram of the garbage collector. Very quickly, there are there is a young generation and the old generation, in which there are two sub generations as well, from and to. There is a minor collection, and then there is a major collection. Minor collection looks at only part of the space, and the major collection looks at the entire heap. That's the difference between the two. Now, the state of the object is actually encoded into the object itself, and there are 4 states. These are well known again: white, gray, black, and red. The intergenerational pointers from old to young are kept track of using write barriers, and write barriers are implemented using cards. So far, it's all standard stuff. Okay, so let's also look at the performance of the concurrent GC that we built. So if you look at the pause and correction times, obviously between the stop the world scheme and the concurrent scheme, you can see that there's a lot of improvement. So you must concentrate on these, actually, these gray ones, so which show you the concurrent pause time versus the rotor pause time. So obviously the concurrent scheme does much better than the stop the world scheme. And then the elapsed time, you should also observe that the y-axis here is really 1, 2, 3, 4. So if you take the average, for some of the programs, the elapsed time actually reduces, whereas for some of them it increases a little bit. But on the whole, the average increase is about 1 to 2%. That's it, not too much. So in other words, concurrent garbage collection does not have too much impact on the runtime of the program itself. Now, let's see the performance of clustering. Now, if there are 4 columns here, of course, there is a big list of the benchmarks that we have run in the paper and the thesis itself, and I have just taken a couple of them to show what exactly is the effect of clustering. So the first column gives you young generation divided, the ratio of young generation to old generation with no clustering. So 2 bar 8, 1 bar 10, etc., etc. The second one is with clustering and the cluster size. So you can observe that whenever the compiler is able to detect clusters effectively, so 2 bar 8 reduces to 0.7 divided bar 1.4, and the maximum cluster size is 3.8. So the total amount of space would be 2 plus 8, and here 0.7 plus 1.4 plus 3.8. That's the way to read it. And here there is plenty of improvement. 1 bar 40, 0.7 bar 1.4, and maximum cluster size is 12.7 MB. Whereas if you look at something like this, the ray trace, it wasn't able to detect any clusters. So there is no difference as such. So in fact, it just allocates a little more cluster, but that adds to the extra size. So in other words, whenever it has been able to detect clusters effectively, the reduction in the amount of space, the generations, and the clusters, the heap size is quite a bit. Whereas if it is not able to detect clusters, there is hardly any impact on the amount of space. Sometimes it may increase a little bit. Then, it's not enough to say we allocate clusters. Well, but how much of actual space is utilized within the cluster itself? So fraction of bytes allocated in the mature object space. The rest of it is actually a waste. So if you look at these programs, for example, 1, 2, these are all really, these programs do very well as far as we are concerned. So something like 80%, 70 to 80% of the dynamic data structures seem to be getting allocated within the cluster area or the mature object space. Whereas if you look at some of these programs, very little of the dynamic data gets allocated in the mature object space. So for some of these programs, this Power TSP and DIRG, stack allocation, that is, you detect that the object dies within the method, and therefore you allocate it on its own stack. That seems to be a much better scheme than trying to allocate as a cluster. So that's the reason we implemented both the schemes, to find out how they do. Now, inter-region pointers. So see, if there are pointers from the mature object space to the heap and vice versa, and the pointers between the young and old generation in the heap itself, these are actually measures, they give you some idea. These are the metrics which can tell you how the garbage collector is really doing. So if you look at that, the percentage reduction in the number of inter-region pointers is phenomenal when the detection of clusters is really very good. And the amount of garbage in the cluster is another indication of how well the scheme is doing, our scheme is doing. Typically it should be 0. In other words, everything lives until the end and then we reclaim it. That's the way it should be. For this ray trace, anyway, we found that it wasn't doing very well, and that's really true here. You see, 99.5% of the garbage is in the cluster. In other words, those objects are all short-living. Since we don't claim it again and again, they just stay put. So we try to experiment with it and see how whether it is true. That's the reason why this 99.5 really appears there. Then, the performance of clustering and the number of collections and so on and so forth. So if we look at it, some of the programs here, we have implemented both the stack and cluster allocation, and that's this both, okay, the bar which corresponds to both. It's always better. So it is at least as good as the cluster scheme. So baseline scheme is here, and then this is the stack allocation only. This is the cluster allocation, and this is the allocation with both cluster and stack. So in some of the cases, the other two, cluster and both, are absent. That is not that we didn't do the experiment there. It's so small that you're not able to plot it. That's it. So with both cluster and stack allocation, the number of collections is very, very small, and therefore we are not able to plot it. Yes. So what is the reduction in collection time? That was the number of collections. Obviously there has to be some a comparison between the number. It should be possible to say that, look, if there is a reduction in the number of collections, the collection time should also go down, and that's true. So you can see that for programs like this BIS, the baseline, this is for both. This is for both. This is just cluster. This is just stack, and this is baseline. All of them take the same amount of time. The 4 parts are approximately equal in size. Whereas for programs of this kind, when you use both schemes, it requires really very little collection time, because most of the objects are in the mature object space, which is hardly collected. It's only taken at the end. And for these programs, it's almost 0. That's why there is nothing to plot, right? So that's the way to read it. What about the pause time? Well, the pause time, again, there is correlation between these. So when for programs of this kind, the pause time of the baseline or with stack, with cluster, or both, it doesn't change. Whereas for programs of this kind, there is a phenomenal improvement. The pause time reduces almost to 0. That's because we hardly do any collection. Unless you do collection, there will be no pause in the program at all. What about the elapsed time? I already showed you something with just concurrent garbage collection. And when you add clustering and so on and so forth, the impact is most of the time the improvement, actually. So the negative impact. In other words, the elapsed time comes down. That's because the garbage collection time goes down. But for some of the programs, it does go up. So there is not much that we can do about it. So here are some of the programs for which it goes up, but it's not really very significant. Now, the garbage collector also copies quite a lot of objects from one space to the other. So how many times copies have been made? The copy count becomes an important metric to measure the effectiveness of garbage collection. So again, it's quite predictable. So if you actually have clusters, most of the time you hardly copy anything, because it's only collected at the end. And for some of the programs, like the BIS, again, there is a little bit of copying still left. So not everything is allocated on the mature object space, and the rest is actually not allocated on the stack either. There is something which remains in the heap, so the garbage collection becomes a necessity. So coming to the end, the clustering optimization reduces the number of collections considerably. It reduces the individual collection times by a reasonable amount. It reduces the number of inter-region pointers. The elapsed time is not affected too much. It reduces the total memory requirement and produces even better results when applied along with the stack optimization. And then what is it that we can do further? What we did right now is, there is only one cluster that is detected. In other words, we really select those methods which are very close to the main program, the calling routine, and then say, look, there is only one mature object space and all the clusters actually go there. Obviously, it's possible to detect the scoped clusters. So the innermost and then the outermost and so on and so forth. And if you recall the Pascal compiler, which was written way back in '73 by Nikolaus Wirth, it used to have PDP-11 implementation used to have a mark and release mechanism for the dynamic objects. So something similar is definitely possible to handle scoped clusters here. And then the compiler can check the usefulness of clustering with more advanced pointer analysis. Well, at this point we don't know what exactly is the analysis needed. So what are the number of cluster to heap references, the fraction of objects allocated on the cluster, dynamic growth of clusters that might contribute garbage within the cluster area. So these are all possibly some metrics which tell us how to do cluster allocation even better. And of course, write barriers are always a problem in every application. I saw the slide one of our colleagues showed here, that write barrier elimination is a problem. Yes, everywhere. So write barriers have to be minimized, so they are inserted to track the cluster to heap references. So elimination improves the elapsed time. So we need to work on that as well. So that's about it, and I can take questions if there are any. Thank you.
Yeah, sorry, I'm confused. You say, well, if I got it right, that you're collecting only at the end of a method, right?
That's right, when the method terminates.
Right, so what if the method is allocating hundreds of megabytes, you just don't collect, right?
No. See, in every program, the dynamic allocation is not exactly known in advance, right? So it's so in every program. So if it's not sufficient, then you need to grow the heap area a little more.
Right, okay.
That's about it. Actually, we don't allocate on the stack. It's actually in the mature object space, which is part of the heap, but not collected by the garbage collector. So you can grow the heap by a linker directive or whatever. You can't. That's always true for every program. So if the because whatever the program is allocating is all that this allocation scheme also does. We are not going to add any more objects. So if the program it requires 100 megabytes, we need to have 100 megabytes of heap space anyway, right? So that's about it. So, and it is certain that the objects which go into the mature object space don't die early. So in other words, that space would have been locked even if we had used the original heap allocation.
But isn't your analysis conservative, inherently conservative?
Yeah, pardon? Yeah, it is. The analysis is conservative.
So you keep things around longer than they would have stayed around with a garbage collector.
Yeah.
So you may not need 100 megabytes or whatever you do.
No, but you see, the 100 megabytes, you're right, in the sense, possibly the scoping would have, if we had detected scoping, and then we would have said possibly 20 megabytes can be recovered right now, and then the rest of it and so on and so forth, it would have reduced. So that's something we haven't done yet. That's true. But if the long-living object says that it requires 100 megabytes, it would definitely require 100 megabytes because we detect it by profiling. That long-living method, not the object. The long-living method requires 100 megabytes. It would definitely have required 100 megabytes even otherwise. We would have missed some allocation possibilities of, like saying the scope regions, but nothing can go wrong really. The longer living method definitely would have required the same amount of space even otherwise.
Yeah, I was curious about one of your slides that you put up that showed, I think, that you could reduce the amount of heap space used.
Right, that's right.
Was that simply because you were moving objects out of a older generation for which you're using copying, so into this this
mature
mature space, which is for which you've only got one copy. So if you had a collector with a Mark Sweep older generation, which many generational collectors are.
Yeah, but you still have to see, if you look at the generational scheme, if you increase the number of generations, you still have to move the objects from one generation to the other, right?
No, I was just saying, if the old generation was a Mark Sweep collector, you wouldn't have to have a copy reserve.
So but the scavenging is still there. So we don't even have to do anything here.
Sure. But
so we don't even have to do anything.
So it's unclear to me just what the heap space requirements of your system are and what the overhead is, because it seems to me that it must increase the space overhead rather than reduce it, unless you choose a particular older generation collector that favours your numbers.
See, the heap reduces because this space, as you correctly said, we are taking out some of the objects which would have gone into the heap. So the heap space is now actually taken by those objects which have very short lifetimes. So the collector becomes much more effective.
So you're not counting the mature space as part of the heap?
No, it's shown separately, right? If you look at the slides, yeah. The cluster size is shown separately. So that's why I said you need to add 0.7 plus 1.4 plus 3.8. That's the total amount of space, whereas here it would be 2 plus 8. That's the way to read it. So we do count the amount of, so the average reduction in heap requirement is about 12.6%. That's it. Taking into account everything, not otherwise. So for example, here it is 1 plus 40, whereas here it's 0.7 plus 1.4 plus 12.7. That's the way the total amount of storage is looked at. So we do show the cluster sizes. The reason why we require less heap is the shorter lifetime of the objects enables the garbage collector to be more effective. It just collects it very quickly. So that's about it. That's the reason it requires less heap now. And the long living objects are not copied from one place to the other, so that in effect has some, improves the pause time and collection time and things of that kind.
Any other questions?
So
Thank you very much.
Thank you.